introduce the talk, and now Carl has started the recording already. Nicholas, the floor is yours.
Thank you very much. Hello, everyone. I'm Dr. Nicholas Wilkinson. I'm kind of still at the University of Leeds in an honorary way, in a different kind of capacity, working on different kinds of things. And I'm an independent researcher working on this as a kind of passion project that's come out of previous work I've done in my MSc and PhD. And I'm kind of trying to reinvigorate it and look into whether I can dedicate some time to it. So I'm kind of trying to sell this as a project idea really at the moment. So it's about balance and about sort of more than balance in the sense gravity resistance in general. But the motivation here is this video. You can watch this as I talk. This little wildebeest calf who's just been born, and he gets up to walk, to stands and walks within minutes, and it does so in a quite sort of goal-directed manner. It's trying to stand up, it's trying to get up, it's trying to walk. And human infants sort of don't do this so quickly, but you can also, watching a human infant learn to walk, they exhibit a similar kind of drive. And so this project really is about asking what is driving or motivating this behavior. Is there a goal? How might one make robots which try to get up and balance like these animals seem to do? And the focus is really on the task definition, or what we call the value function, the cost function, the reward function, rather than on the algorithm optimizing that value. You could use a bunch of different algorithms for that work. Using the active inference formalism, this kind of ties up into something like innate priors. Where do these come from? What if we're talking in active inference framing, what priors are kind of predictively directing these animals to behave in this manner? What's pushing them up? What's making them push up and resist gravity? What kind of normative function or value function? So some active inference work really relevant here is a recent one, priors and predictions, proprioceptive predictions paper. This is the kind of questions we're asking. What are those priors here making these animals behave like this? Let's go to the next page. So the question really at the basis is, what is balance? This is from 2000, but I think it remains true. There's no universally accepted definition of human balance, and people have a kind of intuitive understanding. We all know what we mean, but it's kind of hard to pin down. So what exactly does your sense of balance sense? Is it the same thing you keep when you keep your balance? Is this even valid framing? And if it's not, why isn't it? Some kind of questions to try and open the space of possibilities here. We don't have a great handle on balance to the extent that questions like this aren't obvious and their answers aren't obvious. Is balance some kind of physical condition or state that can be sensed and kept, like body temperature, for example? Or is it just kind of an outcome of other mechanisms, or just an abstraction or an epiphenomenon, or what? Still pretty much mysterious. I think overall, the current view is it's kind of just an outcome, an epiphenomenon of doing a bunch of other things like maintaining your center of mass over your base of support and so on. And if you get all those other things right, you happen to balance as an outcome, or an epiphenomenal kind of designation. And here I'm going to try and argue that it is instead more like a physical condition or state, something that can be sensed and kept, something that can be measured, kind of like body temperature. It's the best analogy I can come up with. And that's the argument I'm going to try and make. And it's quite a long way from what I think is the kind of main current conception. So static balance is well described by just mechanical equilibrium from Newton, wherein all the mechanical forces sum to zero. And this pile of rocks have a nice example. Active animate balance is not so well described because that static balance is literally described as stasis. But we want movement, and stasis and movement are fundamentally opposites. So the forces won't be summing to zero, but we still want to balance. We want to be moving and yet balanced, because this is what animals do. This is what we want robots to do. So maybe we want some way to separate the force generated to resist gravity from the forces we generate to move. That will help to overcome this issue. Ideally, we'd like a kind of well-defined goal state like mechanical equilibrium, but which is fluid and accepting of movement instead of the opposite of movement, and which is biologically plausible. I think it's important that the adaptivity that we observe in animal balance should constrain our explanations. Like this dog was born without his front legs, but learned to walk like this. And I think that tells us something about how flexible and perhaps not this dog has a different species, has a different stance to his species typical stance. So I think we need to bear that in mind as we go along. Is there a goal of balancing? Sort of. So there are kind of operationalizations in terms of postural orientation relative to the vertical, so kind of uprightness, and in terms of postural stability, so kind of not falling down. Most often operationalized in terms of keeping the center of mass over the base of support. So it's a kind of get up and don't fall down pair of goals. And then ultimately, I'm kind of taking this narrative from Massian and colleagues' review here. The goals of balance and postural control are ultimately subsidiary to the goals of volitional action, like support the postures that task or volition wants to take. And thus, I think it's fair to say that balancing is characterized as like a subsidiary sensorimotor control task. And within that broad consensus, there's actually quite a lot of variety about exactly how motor control is executed, is instantiated, but we don't really need to go into that here. We're really in the zone of goals and motivation. So how might we make a robot that wants to get up and balance, wants in very quote marks, to get up and balance like these animals seem to? We need a formal task definition to give some kind of value feedback on learning. We need something like a reward function, an error function. And the two main approaches I've encountered are to define like a target upright posture and penalize distance from this posture. This Morimoto and Doya classic reinforcement learning paper getting an inverted pendulum, 3-joint inverted pendulum to stand up. They just set the upright state as the goal by hand. So you define some kind of upright target posture, and that gives you a normative function. You can penalize distance from that posture. And this corresponds to kind of the classical notion of a genetically determined upright stance typical to the species. and the idea that it's that norm which drives animals to get up, whether when they're born or whether it has with humans later. And then the second approach is to kind of subsume balance as ancillary to other tasks. So maybe you reward distance traveled, so ancillary to locomotion, or if you've got a manual robot, you might reward successful reaching and grasping. So you wrap balance up in some other task, and balance just has to be, the balance task has to be done in order to meet the demands of the task. And that kind of maps to the notion of balance as support to action. This Kuiper's book is kind of the definitive text on that, perhaps. And these seem to constitute the two primary approaches to the motivation of balancing effort in both animals and robots. Oh, by the way, if anyone has questions, do feel free to pipe up as we're going along if something doesn't make sense. So we've got this orientation, uprightness idea. Now, it's obviously very important in balancing, but I'm not convinced that it's fundamental. So, for one thing, animals balance largely regardless of orientation. This lady on the right doing her kind of swim walking is going to demonstrate that orientation is dispensable under certain conditions. Yeah, I'm balanced lying on my couch. I'm still balancing. It's just an easy balancing task. It's not that I'm not balancing. And humans, if you submerge them in water, for example, balancing responses can disappear when there's no load, when the weight is off, regardless of orientation. So humans don't react to the change in orientation unless they're already loaded. And those same balancing reactions can be elicited in horizontal subjects who are supported underwater by imposition of a sort of pretend gravity. So if you push someone against the wall horizontally, you'll get these balancing responses. So they don't seem to depend on orientation. And also fetuses don't seem to maintain, don't seem to try and be upright with respect to the vertical either. But they easily could. So if there was some sort of tendency to maintain a specific postural orientation to the vertical, you'd think that fetuses might do that. But they don't at all. They just take arbitrary orientation. So uprightness seems sort of functionally important, but not fundamentally driving for balance. Whereas the stability, kind of not falling angle, is just pretty definitional. It's typically operationalized in terms of this kind of center of mass over base of support thing. I've just taken this picture from this nice review by Pollock and colleagues. One thing that's worth noting here is that this depends on rigidity. So if the seesaw were not rigid, these people would both end up sitting on the floor, regardless of where the center of gravity were. So just to note that rigidity dependency, because the approach to balance that I'm going to describing, I think, doesn't make the same rigidity assumptions, and so may be useful for understanding non-rigid balance in animals and in robots, soft robotics, for example. I still think there's something missing a bit of what designates these things in practice, upright or not falling, to be good. It's obvious that we need to do that stuff, but we still need some kind of concrete signal to say that these behaviors are good or bad, or that behavior is good or bad for these goals. I don't think we quite get that from these theories. So animals resist gravity, effortfully asserting their bodily form, their 3D bodily form, their 4D behaviour, their balance. Similarly, sort of biophysically necessary behaviours are often understood as homeostasis, like thermo-regulation, for example. But balance seems to be mostly taken as an exception. The main thrust of this argument is that balance is more like thermo-regulation and less like a subsidiary motor control task. So in sort of crude boxological form, on the left here, we've got a sort of, I hope this is a reasonable description of the current view. If it's not, I hope I'll get questions on that. But where balancing is kind of subsumed in sensory motor control. And I'm going to suggest an alternative framing where balance is more an independent or quasi-independent task modality, which is rooted in homeostatic needs, but which recruits sensory motor control components, and also components from elsewhere in the organism. There's not like, I'm not going to go deep into active inference and the free energy principle here because you guys tend to know about that stuff already. And there's these nice papers, a couple of them here I've pointed to by Carl and other colleagues, looking at how active inference can provide a really useful formalism for describing homeostatic systems. And basically these formulations will work just fine for the kind of homeostatic framing of balance that I'm suggesting. Quick word, there's quite a lot of sort of hubbub about and buzz around homeostasis and if it's an adequate description and so on. I really want to situate this in quite a broad sense. There's a nice paper by Bechtel and Bich recently trying to, again, broaden out the notion of homeostasis to something more like its original form before it got very pinned down by the cyberneticists. It's kind of basically negative feedback on set points. So maintaining the internal milieu in conditions amenable to survival. Also want to point to this nice paper by Ezequiel de Paulo, where he shows that essentially closure of the sensory motor loop doesn't seem to be quite enough to give us proper goals, and uses some nice minimal models to show how by developing habits in agents and then perturbing them, you can get more deeply embedded homeostatic behaviors. So, for example, his agents adapt to having their eyes switched in a little Breitenberg vehicle type robots and recover the original behavior of light following, even though their eyes have been switched, rather than just switching the behavior. It's a subtle argument, which I won't go into deeply here, but it's really worth a look with respect to some of these ideas. As I'm going to homeostasis, I just want to briefly sort of use the analogy with thermo-regulation, which I use a lot in this context. Kind of the canonical example. We have a goal range for body temperature. Actions can be deemed good or bad by normative feedback on whether that's this vital goal is being maintained and whether it's under threat. And those signals can motivate the activity of bodily mechanisms to change body temperature, shivering, sweating, finding a warmer place, whatever. I like to separate between goals and set points. The goal being has to be a physical condition, whose feedback just happens physically. So, for example, your body actually being 37 degrees, that's the goal. And it can be proxied by set points, which are internal to the body, which flag deviation from the goal range and perhaps threats to it and trigger responses. But whenever I say goal, I'm talking about an actual physical state like body temperature. Importantly, homeostatic goals are kind of both cause and consequence of lower level self-regulatory activity. So a drop in body temperature causes shivering, which in turn raises body temperature. So you have this nice closed loop macro-organization. Sorry, I've left a couple of sites in here, which helps to coordinate diverse subcomponents into coherent behaviour, service of a shared goal. Homeostatic reinforcement learning is a good example of the sort of setup I'm talking about, and there's some nice active inference instantiations of homeostatic reinforcement learning. That's the kind of instantiation space I'm thinking of for robotics. So if you're going to apprehend and counter fundamental changes such as heat dissipation or gravitational acceleration, you need to somehow calibrate the animal or the robot to properly apprehend and therefore be able to properly counter these biophysical challenges. Homeostasis kind of addresses the persistence of a vital goal state, like body temperature, but not necessarily its origin. So some sort of initial bootstrapping is required to establish the goal state in the first place, and then calibrate bodily set points to effectively proxy it. So, for example, Anna Chaunicker's point that human homeostasis is achieved developmentally through co-homeostasis with another supporting human body is really important here. So, for example, the parental body insulates the fetus against temperature gradients, giving the fetus time and resources to develop its own thermo-regulatory capacities. At birth, the insulation of the parental body is withdrawn, handing over that task to the neonate. And in this way, bodily warmth is kind of directly inherited from uterine warmth. So during that period of being kept warm by the parental body, this is a period during which the fetus can be calibrated to entrench that temperature. Indeed, kind of it would be difficult for it not to be. It comes to rely on this particular range of body temperature, and we'll notice if it's challenged. Another back to DePaulo points out that we can't really give robots true homeostatic needs because they're not alive. But an alternative that could work is the development and perturbation of ingrained habits, which could play a structurally similar role. I may refer back to this argument later. Now, how might animals and robots develop a habit of balancing such that, under active inference framing, they come to expect and predict that they will balance, and in turn act to realize these predictions and hence drive balancing behavior? Carl's recent proprioceptive predictions paper. So other animals face the same problem of living with gravity in different contexts. So fishes, for example, live in water and have the same basic problem, but in a different context. And they often have swim bladders, which they'll inflate to regulate their volume and equalize their density with the water around them. And scuba divers do a similar thing with their buoyancy control device. So it would be nice to have a more general task definition for balancing, which applies regardless of whether you're a fish or a human in water or in air, and which is broader in the sense of encompassing gravity resistance across examples and levels of description, as thermo-regulation kind of does, encompassing active mechanisms from neurons to whole organism behaviour. And there is, Massillon kind of puts his finger on it here, with adaptation to weight is the main task confronting the sensorimotor system after birth. So it's a more fundamental task. It incorporates it's multi-level and extends across examples and levels of description. Applies to fishes, applies to humans, so great. But it's a bit sort of vague to be of much use. It's just sort of trivial, really. And I think this is because weight is not quite the proper domain of description. Conclusively, the weight of the fetus does not change at birth. So it's not a new task. But nonetheless, yes, the load receptors will register more load. And this is because load is a function of buoyancy, and buoyancy does change over the perinatal transition, though not only at birth. Briefly, to ram home how fundamental an issue this is, if you consider an inhomogeneous fluid planet close to equilibrium and relaxing under its own gravity, the matter will all stratify according to density. And if masses are not in their equilibrium stratification, they will fall or rise until they are, just as in oil separating from water. So density gradients which are out of equilibrium will dissipate. The only equilibrium density gradients are these horizontal to the vertical ones. So any animal is a collection of many different ingredients with many different densities. And so one challenge to mechano-regulation, given an inhomogeneous body, is going to be the conservation of a far from equilibrium collection of density gradients. So A here will just fall down, but B, we've wrapped up these density gradients in some sort of container. And on average, the density of that whole container is the same as the density of its medium, which means it can float around in its medium. So here we get an object which is sort of insulated from gravity by its medium by equalizing the mean of its internal component, its internal contents, with the mean of its containing medium. So like you can have a bag of oil and water, and you can make it float in brine, or oil and brine and make it float in water, for example. So you can have density gradients which on their own would dissipate, but wrapped up and contained can be allowed to exist far from equilibrium by equilibrating their mean with that of their medium. So if an object is denser than its fluid medium, it falls down, like an apple in air. This is negative buoyancy. These are the terms I'll use. The opposite is positive buoyancy, an apple in water, or a helium balloon in air examples. When density of object and containing medium is identical, this is neutral buoyancy. And this means the object maintains position relative to its medium, other things being equal, because gravity is accelerating the body and the medium equally. In other words, neutral buoyancy embodies and exemplifies the condition of not falling or staying up. It's the condition where there is no task of balance or gravity resistance. That's why the neutrally buoyant fetus suddenly encounters that task at birth, as Massian says. Usually the formal definition of buoyancy is just the density of the body over the density of the medium. We've reframed this a bit to take the inverse and just swap the denominator. This situates the origin at 0, so that's quite useful. So neutral buoyancy is B body equals 0. And it's useful because it specifies this definition of buoyancy as B body, gives us basically a multiplicative gain term on gravitational acceleration. If B body is 0, i.e. neutral buoyancy, then the body will stay up. So this reframing reflects the inherent biophysical cost of distinguishing oneself from one's medium, sort of a la Schrödinger. And here it's in terms of density. So there's a density gradient between me and the air around me, quite a steep one. And that's the reason why I feel heavy, essentially. Now, amniotic fluid is approximately equidense with the fetus. And so the fetus floats. And intuitively, this neutral buoyancy in amniotic fluid supports the auto-construction of the growing embryo and fetus against gravity. It would obviously be very difficult to grow a fetus if it kept falling down and squashing against the floor. More formally, we can say that the equidense fluid suspension provides a three-dimensional supporting volume in which all configurations of the contained body are unstable equilibria. This poised state accommodates and preserves movement without falling down. So if you move something in neutral buoyancy, it will stay where you moved it to. Whereas if you move something in any other state, it'll fall to the floor or float to the ceiling. And actually, if during pregnancy, if there's not enough amniotic fluid to maintain neutral buoyancy, it's pathological. You get crushed. Fetuses can die from this, or can be sort of crushed out of shape and get clubfoot and all kinds of things. It's really important that the fetus is supported against gravity whilst it's kind of being made. And I think this is a state a bit like being kept warm by the parental body, insulated from temperature gradients, and here insulated from density gradients, and so the task of balance. So it seems like sort of equidense fluid suspension might be quite necessary in practice to growing a complex 3D body and its 4D behaviour. Buoyancy isn't perfectly neutral across term. It seems as if the early fetus might be slightly positively buoyant. And by weeks sort of 20, 26, the fetus is actually bearing a fair bit of its own weight. And that's developmentally important because that loading stress does things like stimulate bone growth, so that the bones will be more ready for their bearing their full weight after birth. On my reading, it's a sort of training stage for postnatal heaviness. You get kind of half heavy, and you get to practice adapting your movements and so on in that sort of easy mode before taking on the full task. Now, because the core organization of the fetus is defined during the period of close to neutral buoyancy, the fetus will develop multiple bodily and behavioral dependencies upon the buoyant force which holds it up. And similarly, behaviors will implicitly expect buoyant support. So say spinal pattern generators generating what will later be locomotor rhythms. All of these things will be afforded buoyant support, and so as they develop their form and shape, they implicitly expect that buoyant support. And these things seem to be quite heavy, especially these spinal pattern generators can be quite strongly conserved across the lifetime. I only know one experimental study which directly manipulated prenatal buoyancy. Was in chicks, and it profoundly altered the developmental pathway. Yasunori Mada did a really nice human fetus computational model, and then removed buoyant support from it, amongst other perturbations. And that really resulted in profound sensorimotor reorganization. So there's not a huge amount of evidence, but what there is suggests that proper development is really, really dependent on this provision of buoyant support. And for the second and even more so the third trimester, the fetus is an active learner, so it will develop sensorimotor predictions, for example, of hand, face, self-touch, and all sorts of things, whose accuracy, again, will implicitly depend upon the buoyant support of the arm's weight. If that buoyant support weren't there, the movement would be different. And then, once the fetus has developed this large, potentially very large set of dependencies and expectations and predictions of its neutral buoyancy condition, those are then challenged by the perinatal transition from amniotic fluid to air. And so this perturbation of all these expectations will cause distributed stressing and destabilization of the fetal milieu, birth, and to some extent the loss of buoyancy before birth will come as a systemic surprise in the Bayesian sense to the expectations of this fetus in a very multi-scale sense. We can talk about the whole fetus, but also to say the bones of the fetus will be suddenly loaded more, and they will respond by micro-cracking and growing in response to that, growing strength in response to that systemic surprise. So this surprise recruits a multimodal assembly of subcomponents whose shared goal is to restore stability of the internal milieu, given this perturbation. And I think it's this perturbation and the body's reaction to it which gives rise to a sort of meaningful and distinct task-based sensorimotor modality of balancing. So not a sensory organ-based modality, but a task-based modality based around compensating this perturbation. So the neonate's first conditioned to expect and predict life in neutral buoyancy, and then challenged to realize those predictions even when that buoyancy condition changes. So active inference is a really good fit, I think, here. But there's a stipulation that these priors, such as the prior for neutral buoyancy, the many bodily set points which implement that prior, must be realized by action and must not change the prior to reduce sensory error. So kind of innateness or permanence, in the same sense that you can't the baby can't react to the dropping of temperature after birth by dropping its expectation of its own temperature and just getting colder. It has to maintain its prediction of 37 degrees or so, such that through action, that vitally necessary condition is preserved. So there's just a particular stipulation on how the active inference has to work there. So just to sort of make this concrete, put it into formal description. So persistence in form and position requires compensating any body medium density gradient. If you're denser than your medium, you'll sink, which means intervening on equation 1, the B-body equation. We can do this by changing the density of the medium, like getting a pool, or by changing the density of the body. And we'll call this approximation. to buoyancy B dash body. So this is an active approximation, or can be. This will tend to zero no matter what, just as water falls through air, but the equilibrium trajectory leads to dissipation and death via being squashed flat. The biophysical task of balance then is actuating this change to the density of the body, density act, such that the body tends to zero whilst conserving the density of the body within viability range. And this demands a non-equilibrium trajectory compatible with the body's persistence and incorporating this active component of work, density act. And there's going to be some subset of viable trajectories which can be achieved in two ways. You can either change the volume of the body, as a fish does in inflating its swim bladder, or you can change the mass, but that's not really easy. It's not easy to dump mass, but can sort of be changed in effect by levering a mechanical force field from a substrate or external force, levering that force across the body surface, as we do by standing on the ground. So for land animals, it's mostly about this act. For sea animals, they mostly use changing their own volume. So you can specify how much excess mass one's going to have to compensate like this, which is just the buoyancy term used as a gain on the mass of the body. So we just get a multiplicative gain control on gravitational acceleration of the body mass. So on this formulation, load appears as a kind of error signal indicating deviation from neutral buoyancy. The baby, the fetus is happily neutrally buoyant and doesn't have to worry about these things until it's not, and it begins to experience load, and that load is a transparent error signal for which directly maps to the density gradient at the organism surface. If that gradient is 0, there's no load, and it increases linearly with load. So this is not neutral buoyancy per se anymore, but effortful mechanoregulation, which is trying to actively emulate neutral buoyancy postnatally by internally replacing the missing ambient buoyant force with internally generated or surface levered mechanical force, thereby cancelling torque from gravitational acceleration. And missing has a specific meaning here. For any given configuration of a massive body, there's a mechanical force field at its surface, which would be provided by the buoyant force of an equidense fluid medium, and which precisely supports body configuration under local gravity. Missing buoyant force is defined by the difference between this notional neutral buoyancy field and the actual current ambient buoyant force field. So to persist in current form and position, any massive body must internally compensate the difference. You can do this passively. A rock on a substrate can do this by passive rigidity, levering that force from the substrate. But for a non-rigid body, it will require negentropic work. And this is the work of balance, whether that be at the level of increasing bone strength or at the level of what we typically call balance, where pushing up from the floor like the baby wildebeest. So this neutral buoyancy equivalent mechanical force field is the goal, I propose, of animate balancing. and it's both what is sensed by the sense of balance and what is kept when one keeps one's balance is a proper physical state and condition. Within that, there's obviously room for a lot of scope of exactly how one goes about sensing, how one goes about maintaining that. But this is an idea at the normative level, really, trying to define the task of balancing. And that pretty much draws me to the end. I've presented the answer, or my answer, to the questions presented at the beginning. I have one other question, which is just for physicists, or directed to the physicists. Seems to me that possibly, anyway, is compensating these density gradients with mechanical force, with endogenous mechanical force, or with buoyancy, with buoyant force, equivalent to compensating local microcurvature in Einsteinian gravity, such that curvature is locally uniform. And if it is that just compensatory, or does it actually eradicate local deviation from global curvature? And I'm wondering this, if it's something like one sort of disappears from, one disappears from gravity a little bit if local curvature is uniform. So there may be, and that will always happen for the neutrally buoyant object. So I'm wondering if there's a useful simplification of some of this quasi-neutral buoyancy goal that I'm suggesting. I'm wondering if there's actually a simpler description in terms of just kind of eradicating local deviations from the curvature of the main local gravitational field. And now I will stop and pass to questions.
Thank you, Nicholas. So the next step is for all of us to unmute and give Nicholas a round of applause for his excellent presentation. Thank you, everyone. So now we open the floor for a Q&A from our audience. Are there any questions, comments, remarks? Feel free to raise your hand with the built-in feature and go ahead. Until, okay, so a farmer, Simon?
Yeah, thank you. But it's one of the clearest explanations I've heard in a long time. I mean, absolutely brilliant thinking about it in terms of buoyancy. In relation to the equation, the act bit is the force brought about by the robot or the human to resist the gravity going down. Yeah, and so one of the questions, and I think a lot of physiologists have overlooked F equals ma quite significantly in relation to what is actually detected by the receptors in muscles and tendons. I mean, it is effectively you have to create a negative acceleration just to stay where you are, and then in order to jump or move, presumably you've got to do the derivative of that, have you not? Is that right? I mean, would you say we're actually in jerk space? If you go in just to derivatives of space, we're already in acceleration just to stand up.
Yes.
And then to move, we've got to be at the rate of the next derivative, haven't we? Would you agree?
Ooh, I might have to think about this more. Are we going in derivatives, or are we?
Well, I suppose it depends if it's smooth or not. It depends if it's, I agree. I can exert more and more force, to, do that, you know. But if I want to go suddenly, like a jump or skip or hop or something like that, then I think I am creating a jerk as
I think
opposed.
maybe that turns out right. So I mean, I was thinking of this in terms of separating movement, which is resisting gravity, versus force, which is being used to resist gravity, and force, which is being used for desired movement. And in fact, maybe that's pans out exactly like that, where the force, which is resisting gravity, is this is one derivative below the force which is used for movement. So that might be a way to sort of actually separate those out formally in a robot. Because
if I have a jumping robot, you know, I mean, I've got to, for a second, just create it. You know, it's got to project itself upwards, right? So that I think there has to be a sort of a rate of change of acceleration almost, doesn't there? To achieve, I mean, it doesn't do it.
Yes. Yes, I think that just makes sense. That just makes sense to me. I'm trying to imagine whether it fits in particularly with one of the concepts I've been using, but I might need to think about that a bit more carefully, whether that actually lines up. But it does mean that there's this, there's a sort of constant which is required, constant effort which is required just not to be squashed flat.
Yeah.
Both at the whole body level and within, you know, our brains have to be floated effectively as well. Every density gradient is going to require some compensation. So there's this like pre-stress that is required just to exist in 3D or to move in 4. And movement will have to come on top of that, and quite possibly from different sources. So you might say that there might be a physiological system which is dedicated to the resisting gravity bit, and there might be a voluntary movement bit. The literature tends to separate these things out, certainly to some extent, and to place the balance part sort of subsidiary to the voluntary movement part. And it might be that rather than one system working on different derivatives, you've sort of got two systems where the movement one is coming along and perturbing things. But yeah, I think
I mean, with walking, for example, I mean, the fall and catch is a good one, isn't it? You know, so you push yourself off balance, and then you save yourself, don't you?
Yeah.
That's kind of that's kind of how. Do you kind of agree with that? I mean, is that how we propel ourselves?
As in lean forward and don't fall over.
Yeah.
So I would say that that's a really nice example of the of how voluntary movement and balance, even if they're separate, quite physiologically separate systems, can work together. So you can voluntarily try and tip yourself, and the balance system will stop you, and by that you can propel yourself, right?
Yeah.
So I think that that makes sense. I had another thing I was going to say, but I forgot it. So I'll come back to it when it comes back to me.
Thanks.
Thank you, Simon.
Thank you, Simon. Any other questions? So just be advised, you're not limited to one question only. You can ask multiple questions, pose multiple comments, and so on.
Please.
So if there are no questions until people gather their thoughts, maybe I attempt one question. So remind me, Nicholas, you called that proposal, like specifically, it was called neutral buoyancy equivalency mechanical force field. That's what you propose as the mechanism. All right. So now trying to translate that into active inference.
Well, it's not the mechanism. It's the goal.
Is the goal? Specifying. Yeah. Okay. All right. Not the mechanism. Yeah. Sure. Is the goals, because you started the talk by saying that we have all these homeostatic loops, but we know there is this drive towards balancing, but how do we encode and express this goal that is balancing itself? All the processes, the physical processes that lead towards balancing. All right. So translating that into active inference. So have you given any thought about what kind of generative model specifications would encode this kind of mechanical forcing, balancing for equivalencing for neutral buoyancy? Because just to be more specific a bit, different species, right, will have very vastly different generative models, given that they have vastly different buoyancies, given vastly different volumes and vastly different body masses. So given also that balancing is such a, I suppose, phylogenetically conserved trait, there is this trade-off. How ancient and how unspecific can a generative model be such that it is conserved across all species, but then also how specific and niche tailored must it be to be able to be functional for a given species? Sorry to take up so much space, but
no, it's
maybe,
a really
it makes sense.
It's a really good question, and I'm really glad you've asked it. So this is why I think that equidense fluid suspension is great, right? Yeah. It doesn't matter what body you put in, it will always work. As long as the body and medium are the same density, then the medium will provide a field of buoyant force suited to that body specifically. And you can see that this works by all the different shapes of mammal that it works for, right? Because you've defined the goal state in terms of a physical condition that you can reproduce, that can be done for the simplest inverted pendulum robot or for a human being. You just have to float them in an equidense medium. And I think this is why it's such a nice sort of technique. It's because it works for arbitrary morphologies, arbitrary sets of behavior that you might develop in that condition, and it's just a bucket of water. Really, you can put a robot, you can submerge a robot in the fluid, and it'll work for that robot. And then you wouldn't have to use an active inference formalism. I just think it's really well suited. The homeostatic reinforcement learning formalism is quite interesting as well. There's a whole, you could choose your algorithms really. But the thing is to learn from experience what balancing is and come to predict the consequences, the bodily consequences of being balanced in the womb passively, because you're passively supported, right? So you learn, it's just learning from example. It's the same as, in other cases, learning from example, that's the training set. And then as the buoyancy of the robot or the fetus is reduced, this is the test set, right? And you just have to recover that state of neutral buoyancy equivalence, which is literally a mechanical force field projected to your surface. At the level of the whole organism. Also, you've got to do all the inside bits. You've got to hold your own brain up with its own fluid and stuff. But you can sort of separate the levels of description by the particular density gradient they're describing. If you're describing the density gradient at the whole body, then we're talking about whole body balance. If we're describing the density gradient at the surface of the brain, then we're talking about balancing the brain in its cerebrospinal fluids. But the fact that basically, it's just a physical necessity. If you do not enact this force field, you are falling or being squashed. And so falling and load is an error signal. And you can pick that up in a million different ways, through a million different behaviors. You could have direct load sensors. You could have your spinal CPGs being perturbed because they're bashing into the floor now or being weighted down. So you're going to have all these perturbations to your expectations across, like the whole body is going to become a detector for deviation from neutral buoyancy, right?
Yeah, Simon, go ahead.
So I'm
If you,
would you argue that at some point the fetus has a sense of falling towards the end of its intrauterine life? I mean, does it start? It starts to. I mean, you've shown that, or you described that. But it will sense gravity.
Yeah, once it's
at
heavy,
some point,
it's contacting the uterine walls. There's less and less. There's less and less amniotic fluid. It's less and less insulated from the gravitational gradient. It's going to start feeling that heaviness.
So even though it's upside, so before it's born, it's generally upside down, right?
If things are going well.
So, but you're arguing that it may have a proto sense of what it is to fall over.
Yeah.
I can detect the error signal. Yeah.
Yeah. So the vestibular system is sort of proto-functional from like 20 weeks or so.
Yeah.
About the same time or just before the babies start to lose buoyancy. So there is some ability to pick up the direction.
Yeah, and certainly head control in the first 6 to 8 weeks is really important. You know,
you can, and then there's going to be things like feeling the uterine wall against your back or your feet or whatever, and they feel it in their bones. So there's experimental evidence now that babies who have too much amniotic fluid in that final trimester, their bones don't grow as strongly and as well.
Yeah.
Because they need that loading to spur the growth. And they get similar problems with preemie babies who are born very early and they haven't had this kind of gravity training, easy mode time, and they can get this brittle bone disease where their bones are not strong enough to hold up their body. So it does seem to be quite important that the body is trained gradually into getting stronger and being able to hold a bit more of its own weight before it's like chucked out and made to hold up the whole thing.
Good. Thank you, Simon. Are there any other questions? Just Andrew King, sure, go ahead.
Hello, Nicholas. This is absolutely fascinating. Thank you for this. I'm a physiotherapist. I'm not a physicist. And rather than the inter species comparisons that were being made before, just within human beings, it seems to me that there is a difference in postural set, one individual to another. Huge, well, not a huge, but there are differences in individuals in how taut their muscles are. Is what you're saying that that is a prior that you set in pregnancy, or is it changeable after pregnancy? I'll give you an example. I used to have a student kind of in my group of physiotherapy students who was very floppy. She used to, you turn around and she was the one who was all with her head on the pillow, and she was an international athlete. She used to go along to a wind tunnel once a week, but in order to throw herself off and practice her free fall flying. And I've always wondered whether this was her selection dictated by her postural set, or whether her postural set was dictated by what she practiced.
Wow. So I want very speculatively, it seems possible that there's individual differences in the time course of buoyancy over pregnancy. Seem to start off slightly positively buoyant, end up holding 60% of your own weight towards the end of pregnancy, and it gradually decreases. The support you get decreases over time, and that's individual. So some babies get that drop week 21, others at week 26, and it's conceivable that individual differences in that developmental trajectory of buoyancy are going to have lasting effects. It's conceivable. I don't think it's necessary. You could equally, it will have effects at a time, but I don't know that it would need to turn into anything permanent. you might have kind of attractors in that process where everyone basically, all the typically developings end up in the same place and start again. Or you might have quite a trajectory dependent sort of individual postural set developing. I think there's scope for it, but there's at this stage certainly no evidence as far as I know. But it's exactly the sort of question that I would like to start asking by introducing this sort of framing of what balance is about.
All right. Thank you, Andrew. Any other questions? Okay, Simon, go ahead.
Yeah, just one last thing on, learning to move. Obviously the baby or the toddler, often is supported, aren't they, in the old way of trying to get your kids to stand and walk. They're in a little thing on a bouncer or something like that. They kick their legs up and down, enjoy getting off the ground, coming back down with some buoyancy produced by a spring. I mean, it's obviously a very easy thing to study. You can change the buoyancy in a typically developing child learning how to stand and walk. My question was more around the Bernstein freezing and freeing of degrees of freedom and the ability to drive a system towards. I mean, I've had a little bit of experience with my friend Luc Berthouz on bouncing robots and how a robot learns to jump a bit like a child in a spring. I mean, this work was done quite a long time ago, but the Bernstein idea was quite relevant. That you go quicker towards the where you want to end up, or where the robot wants to end up, which is to have a multi-limb form of bouncing, and the same goes for swinging in a getting the robot to swing. I mean, when we learn to swing, we fix our legs and we go like that, and after a while you can do it, and the same with pistol shooting. All this, but no, I was just wondering whether you were thinking of extending into that area, or is this too sort of, if you like, close to the mechanism of learning for you, or perhaps it's not relevant at all? I don't know.
Luc Berthouz was my master's supervisor.
Who was?
Luc Berthouz was my master's supervisor, and he supervised.
Wow. Right. Okay.
And this was my master's project.
Oh, I didn't know that.
Okay. But it's better work now than it was in my master's. As he says, now it's a clear explanation. It wasn't at the time.
So what was a clear explanation?
If you said that this was a nice, clear explanation now, but I must admit it wasn't as clear an explanation.
Well, I'm not sure. I think it was a clear explanation. I just like looking at Luke's videos, and.
But so Luke was my supervisor for when sort of my original foray into this space.
Okay.
In my masters at Sussex. So I think that stuff's really interesting. I think there's lots of possible applications of having a good normative theory of what balancing is. If we can define the task well, I think we can benefit in all sorts of contexts. So certainly something like, say, a bouncing robot. If you were to can imagine a robot in its prenatal state, you might give it some bouncing appendages. Maybe it's got some controllable springs, I don't know, or some complicated legs, whatever. And you can imagine having it learning some rhythmic movement of its springs in neutral buoyancy, and that's its natural frequency. And then you could make the fluid medium a bit less dense, and it will float down a bit, and it will have to export a little bit of energy to get that rhythm going again, and make it a bit heavier, and it will learn gradually that it has to add its own gravity resistance bit to the process. And then you could take it out of the womb, the box, and stick it on a table, bearing its full weight, and it'll have, you know, a little motor program, little sensory motor program there to deal with this sort of thing, and it just has to do a little bit more adaptation. There's a really nice study on piglets, actually, like precocial walking in piglets, where they there's a link on one of the pages in the presentation, and they're basically looking at adaptation of these inborn prenatal motor components to this rapid precocial walking that they do, and it's kind of it's what I would expect from my suggestion here, which is that they have this prenatal repertoire, which is it's quite kind of pendular, in that it's got particular biomechanical form, and it's dependent on the buoyant support that's received, and they have to rapidly adapt those prenatal components with additional components. So on my view, those prenatal components have to be conserved, because they're going to be driving, staying up the whole time, and you have to add new components on top in order to conserve them. And it seems like those piglets are doing something along those lines when they're, you know, rapidly adapting those prenatal, just rhythmic movement components into the sort of repurposing them, utilizing them for walking, which is a kind of walking ends up looking like a sort of settling point between preserving those prenatal components and interacting with the substrate, rather than walking being a kind of goal in itself. It looks like something you're sort of stabilizing those prenatal behaviors in the postnatal environment. That's where you end up with this locomotor gait.
Okay, very interesting. Thank you.
Thank you, Simon. Any other questions? If there are, okay, so Mark
Yeah,
Robert.
so I'm also
questions?
a physical therapist. Yeah, I'm also the great job. So I'm also obsessed with balance, but I really like how you went all the way back to the womb and the prenatal state to conceptualize this problem. I think that's fascinating. I hadn't thought about it in those terms before. But it sounds like, and so this is just more of a clarification, like early on, there's just a general expectation of buoyancy, right? That we can say is essentially balance, right? And it's regardless of position, is that right?
Yeah. I mean, if you're in a swimming pool and it's equidense, doesn't matter what pose you take, you'll just hang there, right?
So then it gets more specific as there's this, I would say, graded exposure, right? There's less and less buoyancy as the amniotic fluid subsides, right? And so and then that's conceptualized as a prior.
Mm-hmm.
So that's very interesting. I also wonder how the mother's movement impacts the prenate in that situation, and that must somehow become internalized as a prior.
Yeah, I think that's a really interesting question. There might be a bit of work on that nowadays with some of the sort of imaging advances that have come along. You can certainly imagine a situation where rhythmic movements of the mother are relevant to the development of rhythmic movements in the fetus. Fluid dynamics are complex. Like, you know, if you turn around your soup, you never get to the other side, right? The soup stays still in your bowl. And so exactly how maternal movements are going to are going to impinge on the fetus, it just has to be looked at kind of experimentally. It's quite difficult to penetrate exactly how important they might be, if they're useful or if they're kind of disturbances. I think it'd be super interesting to look at, but I can't really kind of imagineer my way into it with any confidence.
Okay. Another thing you mentioned early on was, I think, has to do with the the precision weighting of the expectancies, right, of the generative model, because you were saying that there is no, essentially there is no belief updating, right? There should not be a model update that
That's
goes
right.
in that direction, although we do probably see that as we age, right? There is this sort of model update when one becomes unsuccessful with balance. But this is something, and I think this will probably get clarified as Carl jumps in, but I think it has to do with the precision weighting and the expected precision being almost set to, you know, a completely high confidence zone,
One.
right? That they're it's one, right?
Right.
And so what does that do to the I would say the prediction errors at that point? Does it disregard them?
Yeah, I mean, turns them into sensations. I don't know.
Okay.
Like
Calibration signals, maybe.
Yeah, to use the thermo-regulation analogy again, like the baby comes out, gets cold. The air out there is colder than takes the warmth away more than the ambient in the womb, and they feel that as cold, but they don't adjust the priors on body temperature to get cold with the room. They keep their priors on body temperature. And it's the same kind of situation that I'd want to propose here. And the other thing is you can accommodate some error. It's okay to make a little bit of error in these things. It's just not okay to make too much. You know, your body temperature can fluctuate a bit within range. It can even be pushed out of range to run a fever or something. Maybe that's adaptive. We go up and down all the time. We don't keep this mechanical force field precise. We allow it to shift, and we kind of skilled movement actually uses that the gravitational acceleration quite well. Roger Federer is this sort of classic example of someone who uses gravity in his movements to make them smoother and make them more efficient and so on. See the way he like drops his racket just before he hits to get under the ball and stuff. It's beautiful. So certainly there's room for play, but you can't afford to fall or be squashed indefinitely. So there are hard limits as well, right?
Thank you. That's a great explanation.
Thank you, Mark. Are there any other questions? So if not, I'll just maybe venture a last question. So Nicholas, as far as I could tell, your formulations seem to be continuum mechanical. I am curious, since you mentioned robots, how would it generalize? How scale invariant or scale independent would it be when you consider that for robots, which have these articulations, or even for insects with multi-segment bodies, it's local joint torques that dictate the balancing problem and which is the control target, rather than the distribution of the forces of the body forces, as in a neonate case or in a fetus case, or even our case. So
yes. Well, really, this is the kind of question I want to be able to ask in a research program, right? I would say that the sort of biophysical necessity of maintaining that force field just holds. It holds if you're a rock.
it holds. Yeah, but that's very general, right? It doesn't constrain too much the theory.
Yes,
that's the point.
But how definitive is that of the task, and how much, or how much is it more defined by the biomechanics of the particular embodiment? Mm-hmm. There's going to be a lot of trade-off here, I think. A lot of the time, maintaining that force field will just be built into the rigidity of the exoskeleton, will be built into the rigidity of the limbs and so on, and will be implicit and kind of passive in terms of motor control.
Yeah.
And then maybe you're just dealing more with those joint torque becomes much more important, and that mechanical force field, it being a goal, becomes less important. It can be approached more as an outcome, perhaps. You know, if you're perfectly rigid, you can approach it as an outcome, as a rock, as a rock can. But as you become more less rigid, as you become softer, you have to pay more and more attention to it as a goal, because it ceases to happen passively. So we have to be full of fluid pressure, for example, to keep our our soft bodies inflated and keep that force field going, whereas the ant has an exoskeleton. This is done by rigidity.
Interesting, very interesting. Yeah, no, that at least when you're talking right now, I made a connection with evolutionary pressures towards endothermy. So soft bodies with liquids in them are very good for heating you up endogenously without relying on exogenous sources of heatings. So it might be like your hypothesis would become a goal in those lineages and clades that are also endothermic more, because they need to be soft, full of liquids to be able to produce temperature internally. So yeah. All right, so these being the questions in the Q&A session, I think it's Carl's turn right now.
Thank you. Could I just excuse myself for a minute or so? I'll be back in a tick.
Yeah, sure.
Before we move on to the next session.
Yes.
I think the chair needs to have a musical instrument at this point.
Yeah,
keep us all entertained.
Just thinking the same thing.
Unfortunately, I cannot play anything. I am good with words probably, but not with instruments, with musical instruments. Usually we have no break. It's full on 2 hours plus, sometimes 3.
Thank you.
Yeah, right. So I think it's Carl turns right now.
Good. So after the break, it's my turn now, is it?
It is, Carl, with a bit delay.
Okay. Well, yeah, that was a wonderful presentation and particularly rich discussion. So I think a lot of the key issues have already been covered. I'm going to focus on some of the sort of more technical, theoretical aspects, and with a view to what you might want to do in terms of empirically pursuing this as a scientific endeavor, or possibly leveraging the idea in terms of a product or a way of augmenting the training of things that balance. And just before I forget, it also seems very relevant to space technology and astronauts and how they deal with coming back to to Earth after a period of weightlessness. So a number of domains of interesting application here. But just to pick up on the last few questions, and the focus on rigidity and the importance of precision in terms of how you balance the tendency to adjust your world model to fit the sensory evidence at hand, as opposed to how you reflexively change the world to match your predictions. And that seems well. Let me first of all grab the screen and just then I use my little papers and icons to remind me what needs to be said. Oh, that's not really what we want. What we wanted is the I'm always mindful, just in terms of the overall thesis that evolution has endowed us with the right kinds of bodies to make the buoyancy argument very plausible. I'm always mindful of those kinds of systems that show very biomimetic kinds of behavior, the kind that Rodney Brooks would champion, for example, in promoting radical inactivism. But have you seen these examples from this Dutch artist building wind beasts?
Yes, they're wonderful. And this tensegrity robotics has kind of copied these ideas quite big. And in the last 5 years, there's lots of tensegrity robotics. It's super exciting. But they're interesting to control.
I was rather hoping to see what for those people who haven't seen it. There we are. So they're just spontaneously walking. So there's no control. There's no anything apart from a little bit of wind. It just basically rolls downhill. But of course, there is no hill for it to roll. That's provided by the wind. So I just put that up for sort of visual entertainment. Let me just
They're wonderful.
There we go. And of course, there are lots of wonderful videos in terms of simulating this kind of thing using, and this is, I think it was Dreamer 3. This is Daniel Hafner's Dreamer. Using it is actually using reinforcement learning, but interestingly, the objective function that Daniel Hafner uses to train these little robots to walk around and to learn to walk around is actually very, very close to the active inference objective function. So he has a sort of KL divergence kind of objective function that also, to a certain extent, includes expected information gain. So this is like reinforcement learning of a very nuanced kind that's getting very close to. It's not quite the same as active inference, but it is active inference. And I'm just putting this up just to remind myself that should you want to engage with with people demonstrating proof of principles as to what the sort of buoyancy notion would bring to the table, one forum in which you could demonstrate the importance of having these innate priors in play will be to show that you can massively accelerate the learning of purposeful locomotive behaviors by first training the agent in a bath in utero.
Yes, that's kind of one of the main messages. Really, it's not a very complicated message. It's easier. It's a bit like there's a lot of rehabilitation stuff that uses pools to help rehabilitation, and yeah, I think so. The current robots tend to start off with random flailing, and then they get some rewards, and gradually behavior will adapt as the rewards come in. But the baby wildebeest doesn't start off with random flailing. It starts off trying to stand up, and I'm trying to bridge that gap with these innate priors, essentially.
Yeah, well, I think you've already bridged it. I was thinking more along the lines of demonstrating to other people using standard benchmarks or simulation environment physics engines to show how you can get this remarkable behavior from scratch, just with the right kind, with the right kind of innate priors. And you said it, if you just train, provide a training set that is in is in the swimming pool, and then transfer to outside the swimming pool, with the correct engineering of the robotics control, in the spirit of active inference and the equilibrium point hypothesis, you should get immediately that kind of behavior for free, with a little caveat. So perhaps that's the best way to frame my feedback, with two caveats. So one caveat is that and it is that there is stuff to be learned, I think, after you come out of the womb, and in a simulation environment, when moving from the training to the test scenarios, when you put gravity in play. So that's one theme I want to address, and the other theme I want to address is you don't need random movement, and that speaks to your observation that in the third trimester there's empirical evidence for active learning, and I would submit that the active learning is the driver of actually moving, even in the context of this buoyant, balanced for free environment. And well, let me just dismiss that as a sort of a point of conversation, and just motivate it with some recent work from Scott Kelso. So this was published a few weeks or months ago in PNAS, and it was a sort of drilling down on the motor behavior of neonates and infants and asking what causes them to move, and specifically looking at the baby mobile paradigm. So this is, if you like, asking why do babies like rattling their rattles or moving their mobiles when they're in the cot? Because the conventional notion is that they just like stimulation, and that if they can cause a rattle to make a noise or to move in a particular way, then that is reinforcing. So this would be the reinforcement learning paradigm. The active inference view is no, that's not the explanation. The explanation is intrinsic motivation you find in neurobotics, and it is basically choosing those actions that will resolve the most uncertainty about the cause-effect structure of the world you find yourself in. And what would that mean for the baby mobile paradigm? Well, if the reinforcement learning perspective was correct, then you'd expect as soon as the baby realized and learned that moving their leg that is tethered with some cotton to the baby mobile caused the mobile to produce auditory and visual input, that it found extrinsically rewarding, then it would just keep on going. It would just try to elicit as much stimulation or exteroceptive stimulation as possible. Whereas the active inference approach would say, no, the best kind of data to disambiguate whether you caused that or it was caused exogenously, possibly by mother or possibly by some other non-autonomous cause, would be to rattle and then stop, and then rattle and then stop. And that's the best experiment, the best data that you could possibly get in order to resolve your uncertainty about the hypothesis, I caused that or I didn't cause that. And in fact, when you look at this empirically, that's exactly what babies do. So Scott Kelso and his team, particularly Lisa here, are currently simulating the baby mobile paradigm and then fitting a synthetic baby who's operating under active inference with the active learning, which basically is replacing a reward function with an expected information gain, and then matching the parameters, the hyperpriors of the synthetic baby to match the actual performance of real babies. So they haven't actually published that, but it's a wonderful use of computational phenotyping, really drilling down on what causes movement, and under active inference, the cause of the movement is that which is intrinsically motivated to disclose as much evidence as you can that's going to resolve your fundamental hypotheses. Am I an agent or am I not? Am I in charge of my limbs, my world, indeed my mother or not? So I didn't realise, and it's really interesting to hear that this is going on in the third trimester. I didn't know that. So it's really quite interesting, as you say. So that advances in in utero imaging that becomes a really, I think, appealing empirical direction of travel. Anyway, I just wanted to sort of highlight that the one way in which you could actually push back against your assertion, you could choose any kind of model predictive control, and this would work. I will push back against that. I don't think it would work. I think you'd actually have to go to the full active inference objective function to get the intrinsic motivation that can now be realized in the context of buoyancy. And then that would give you, I think, a more complete story as to how babies learn to learn their world and what parts of the world can be controllable. So that was my.
No, I agree. I agree. It would be possible to use all sorts of algorithms and it not be quite as good, and you could still have a go. But I think active inference has the internal consistency for a start, and the scope, and then it has this additional information seeking aspect, which doesn't come from the sort of buoyancy homeostasis part. So I think they fit together really nicely with basically you're doing active inference, and the whole buoyancy thing is just a bit of historical context, isn't it?
Well, I think yes, it's just a bit of historical context, but it's also fundamental in terms of providing the context and the priors where you can actually now realize those intrinsically motivated epistemic affordances, even in utero. I think that's the story here. That there is a sort of a co-evolutionary story or a separation of timescales that really. So yeah, it's fine to be intrinsically motivated and to do active learning, but if you can't move because gravity's flattened you, there's no point. There's no point in knowing that it's possible to do active learning. So I think there's a lovely interaction there, which puts one in the context of the other. Undermining what I just said, that you have to use active inference, I'm now going to say the opposite, that I think when it comes down to the actual mechanics of moving, I agree entirely. You could use model predictive control, you could appeal to the equilibrium point hypothesis, you could even appeal to perceptual control theory as alternative frameworks that all would work very nicely in the context of the importance of this of the buoyancy argument. And I think all of those, in contrast to in forward inverse modeling and motor control theory that we saw in the 1990s, all of those just rest upon minimizing prediction errors in observation space, in outcome space. So if you can predict what you should feel, then you just let your reflexes do the work, and in an elemental sense, that's just a statement of model predictive control. It's just a statement of perceptual control. One way of looking at perceptual control theory, and of course from a physiological point of view, it's just a reversion to the equilibrium point hypothesis in the 1980s before people got distracted by forward inverse models. From the point of view of our conversation, though, I think it starts to it does raise an interesting question, because let me just get rid of the we've done that, so we don't need to do that. What we did, yeah, this is the paper, and I just to sort of the reason I put this paper up, which is the very first description of active inference under free energy minimization, is that the majority of this paper was all about oh, well, not the majority, but one of the first things that hits you is this natural resistance to perturbations that emerges from this offloading of motor control to motor reflexes, so that now the set points are just the predictions you have under some kind of forward model or generative model. And if you get that right, and of course from our point of view, getting it right is what you would learn when you're in the womb, when you're buoyant, when you're floating around and balancing in an optimal way. If you get that right, everything else will follow. And crucially, and you actually said this explicitly, you will get this natural compensation or resistance to or resilience to perturbations, whatever they are. So, as soon as something comes along that violates your expectations, your reflexes will just counter them until your expectations or your predictions of the set point are now again realized. And the analysis in this paper foregrounded the important observation, which you've also just been rehearsing in the conversation, that the ability, this resilience to perturbations, such as being born, rests upon the relative precision that you're affording your predictions relative to the sensory evidence or the prediction errors that are actually observed. And I think that's a really important point. And I think it's important, just from the point of view, if you wanted to simulate this, if you wanted to actually simulate active learning in utero, and then see how that learning was inherited by behavior after birth, then one's going to have to demonstrate the utility of that, one's going to have to pay particular attention to the precision or the gain afforded the priors that are learned relative to the prediction errors before and after the perturbation of being born. The reason I think that's important is that, if just coming back to this Robert's observation, that the actual sensory space, the sort of the space in which you've got your equilibrium points or your model predictive control, is not the space of forces. It is the space of proprioception. And that proprioception is largely going to be driven by stretch receptors and pressure sensors. And I've never thought about this deeply until this presentation, but there seems to be, and this is sort of half a question, which you don't feel obliged to answer, but it seems to me that the model predictive control, or the sort of the active inference formulation, where you're just offloading everything to the reflexes, works absolutely fine if we just limit the proprioception to pose information, the proprioception limited to joint angles and the like, and stretch receptors from the muscles and from the tendons. So if I believe that my active learning and my epistemic foraging entails sensations from my motor plant as if I had no weight because I was buoyant, then when I'm now put into the real world without my amniotic fluid, then I can just reproduce those very precise beliefs about that kind of proprioception, no problem, and I will be I will just continue to stand up and walk around or do my active learning as if I was buoyant. But that does not apply to pressure. You talked about sort of sensing contacts with the womb and the like. So the pressure that I sense will change profoundly after birth, which suggests to me that what you have at hand is a very selective assignment of high precision to the pose and proprioceptive channels that report the position of the limbs, but you have low precision on the priors that are predicting the pressure, or low precision on the prediction errors of pressure sensors, so that you can learn now the after birth predictions of what I should sense in terms of the pressure, whilst maintaining the actual the buoyancy like pose and locomotion that is being driven by the externalized prediction errors in purely the proprioceptive as opposed to the precision and possibly even vestibular inputs. Just to address sort of Mark's comment in terms of how mechanistically these precisions are implemented, what I like to think of is that you've got your sort of you've got your reflexes down in the spinal cord, and you've got the central nervous system, and there is a prediction error. Or imagine that there is now a mismatch between the top-down descending predictions and the primary afferents reporting proprioceptive position of the limbs, say in the alpha motor neurons. And then this prediction error can go in one of two directions. It can either be attenuated from the point of view of the CNS, so that you're attenuating the broadcast of that prediction error up to the CNS so that you change your mind and you change your temperature, for example. Sorry, you change your prior beliefs about the temperature you have or the pose that you are currently exhibiting. Or if you attenuate the precision of those ascending prediction errors, the prediction error then is forced to drive the reflex arc. So, and that sort of balance, whether you send your prediction errors upwards to revise your beliefs about the pose of your body versus driving the motor plant via reflexes to realize the predicted pose of your body, is just the precision control we're talking about. So it's a balance whether you send it up or not, and not sending it up would be sensory attenuation that is necessary to realize movement by using the prediction errors to drive the reflex arcs. That kind of story, though, would, I think, have to be nuanced when we're talking about the sensory attenuation of pressure sensation as opposed to proprioception purely in terms of joint angles and the like, because you do want to actually change your mind about pressure, and you do want to now learn how to move your pose or explain why it is now that you know, when I'm in contact with a surface, I feel more pressure than when I was buoyant, and that's, I think, that's part of this active learning. I think that would I think be both simply simulated by assigning a very, very high precision to that kind of proprioception that did not change before and after birth, whereas you would have a relatively lower precision on those proprioceptive somatosensory inputs that did change, even if the behaviour was exactly the same, even if the locomotion was exactly the same. And you could lump that under the active learning. So, you know, I think that would be a really interesting thing to simulate. To my knowledge, it's never been simulated. So, well, let me sort of stop wittering on. And
that would be a really nice thing to look at, actually. I think viscosity provides another sort of variable that would be an interesting comparator, because we have the viscosity of the amniotic fluid and the low viscosity of air. But we don't seem to try to preserve movement in a viscous state. So it's another like interesting control variable where you've got this perturbation, and some of the perturbations are treated as vitally important to correct or to compensate, and some of the perturbations aren't. So yeah, it's going to get complicated in the event of a complicated body, right? That's for sure. I really like the idea of taking some of those earlier, like the little guy walking up the steps, and sort of repeating that with some pre-training in a pool. I think that might be a really nice little demo, actually.
Could I ask you, and perhaps Simon and Mark will know, because then we've also got the vestibular system, which, so if we just forget about the physics, and I realize that we haven't got a physicist here who can answer your question about are you eliminating global curvature locally? I suspect you are, but I actually want to move away from that and think about what the signals are. What is the intrinsic space, the sensory space that would be subsumed into proprioception and somatosensory input. So I've got stretch receptors, I've got pressure sensors, and I've got vestibular input. What else have I got? Does anybody else know what else?
Yeah. So you've got the stretch receptors are dynamic and static, right? So there you've got muscle spindles, bag and chain type. So one will look at the rate of change of, so the stretch reflex is basically rate of change of length of the muscle, gives you the 1A stretch reflex. The static, i.e. the just having a muscle at length A versus length B, comes through the type 2, what I think they call 1Bs, and then you've got tendon receptors, which are the Golgi tendon organs, which are mainly force detectors. All right, so what I said in the chat was that it just dawned on me as we were chatting about the fact that obviously when the baby's born, the force receptors start to detect something, but when it's in neutral buoyancy, it will still get some form of proprioceptive feedback just from stretch. So if it just extends or kicks its legs in utero, the muscles will extend, will lengthen, and that will give you a feedback through these type the classic Sherringtonian stretch reflex and the type 2s, which are just the static receptors. So even if there's no external force being applied, there is still because it's always, I always think it's just weird, why we have these stretch reflexes. What are they for? Why not just have a force detector? Why have something in the muscle itself that's detecting length? Obviously, there's proprioceptive value from knowing how much our muscles have been stretched. But why do we have to then produce an opposite response to shorten the muscle, which is a tendon reflex? That always was quite mysterious. But it is interesting that obviously I get the error bit. You can get the errors, and learning, through minimization of the error in relation to a reflex. But it is interesting that, of course, a stretch reflex would work in neutral buoyancy, whereas a force detector wouldn't. Does that help us?
That is interesting.
Can you tell what do these force detectors? How do they work then?
How do they work? That's a good question. I'd have to look that up. They sit in tendons, so they don't require stretch per se. They would be. There must be some deformation to detect force, but they don't. They don't have anything like the sort of lengthening and shortening that occur in muscle spindles. So they sit in tendons, a bit like a pressure receptor, I imagine, in the skin. I think.
I see. Right,
so
right.
I think of them as being literally they're turned on and off by changes in the local force. Just as you know, if you put your hand on the table and you push down, you know, you've got a Purkinje they call their something capsules anyway, and they so I think they're more like that. I'd have to look it up. Whereas the spindles are very, very specific, and they also are controlled by a muscle, you know, so they have a thing called the intrafusor muscle, which is a gamma input, which tends to go with the alpha motor neurons. So basically, you get gamma alpha coactivation, so that basically as the muscle is contracted, the spindle is then tuned to detect stretch, but by shortening, basically. I mean, it will lengthen and shorten just as the muscle fiber lengthens and shortens, and that's controlled by another set of motor neurons. So I think they're very different animals. But of course, both will give you error.
And that it is that exact difference I was trying to get at with sort of the difference between reporting pose versus reporting pressure. And the pose you need to, if you like, maintain after birth, whereas the pressure you don't want to, you know, you're going to have to learn a new set of predictions.
Yeah, it's a new thing. For pressure's new. Yeah. And of course, most of the learning must. I mean, it's great that there's intrauterine learning of pressure, but it can't be anything like what it's like to be born and then on two legs, you know, and of course it takes a long time to get head control through the vestibular system, and loss of head control is a real warning sign for, you know, a child with developmental motor problems. But all of these are, you know, resisting gravity, aren't they? You know, the head's very heavy, and then finally standing and walking. So it's fascinating, isn't it? What I love about this is you know how interesting it is, you know, in terms of the buoyancy way of looking at it.
And add vision when we're born, right? And so it kind of takes me back to one of your initial slides that was talking about the classical model of the motor control problem of like some kind of conscious control is what I think you were getting at. I forget, executive control. I was like, I would fall over. That's way too much. I never thought about all of these inputs as some of them being brand new, like vision and pressure becoming relatively novel inputs. And then you were asking about the vestibular inputs. So now we've got being able to detect linear and angular acceleration through the vestibules and semicircular canals, respectively. It's quite a puzzle.
Well, I think the vestibular thing is going to be super useful because, so if you're neutrally buoyant, you're still getting the vertical, right, from your vestibular system. It doesn't rely on the load. So that can be operational, but not associated with falling down when you're free floating. And only when you begin to lose buoyancy, all these loading effects will start to correlate with that vestibular system. So with that vestibular signal, and so the perturbation kind of recruits the vestibular system to explanation of all these new goings on, and there's quite cool evidence, I think from mice in particular, of vestibular disorders, deliberate ones that the experimenter does, really disrupting the development of sense of self and integration. And I think there might be an important thing there where the vestibular system ends up being a kind of hub, this very reliable plumb line for the vertical, which all these distributed bodily things of my bones being heavy and my arms falling down, my head falling down, all these things then start to correlate with this very reliable plumb line signal. And I can imagine that without having that kind of this grounded hub of sensing the vertical, it would be very difficult to bring all that stuff together. But it's still only a sense. It's not like an essential thing. It's just telling you some information. So, for example, if I go scuba diving, I can happily go upside down and continue all this stuff in completely opposite or horizontally to the vestibular. it's this plumb line sense, but it's not demanding anything of me. It's just giving me the dimensions, just describing the first dimension, and everything can then be compared to that. But I suspect, so the idea that a sort of upright posture is the key to pushing an animal up. I don't think it quite works, because you could turn someone upside down in a pool, right? And if you put them in a pool of brine, they could even be pushed upwards, and they would have to resist that just in the same way that they have to resist gravity the other way up. So the vestibular thing seems like something you can afford. It's just sensory grounding, but doesn't need to be, or doesn't work particularly well as a normative grounding, saying you should have this relationship to gravity. It's more like just define the dimension and everything else can relate to that, but it's not that verticality that's motivating this resistance to gravity. It's a load that's motivating that resistance to gravity. Which for some people is controversial. Some people think that the vestibular system is really the sense of balance. It's the most important thing, and it's the definitive sense which allows us to do all the other stuff. I think it's recruited to balance by the loss of buoyancy.
All right. So, Carl, are you finished with your feedback?
Yes. No, I'm just thinking. I think the last part, yeah, sort of. And it speaks to the sort of the enormous challenge of multimodal integration and multisensory integration and learning at the point of birth, because you only have to put these things together in context after you're born. I was just thinking it's interesting that most unborn things have their eyes closed, or they are precluded or sequestered behind their eggshell, so they don't have to worry about vestibular and visual integration until it really matters when you're out there wandering around.
Yes.
So
I have one last thing I'd like to say, is that I want to get some funding for this project, basically. So if any of you know anyone, ideally in France, because that's where I live right now, who might be interested in hosting this project at a lab and maybe applying for some funding, please do put the word out, and that maybe direct them to this presentation once it's up online.
The only people I know would be Jérémy Matou in Lyon. Jérémy Matou, M-A-T-T.
Jérémy Matou. He's in Lyon. That's perfect, because I live in Lyon. Do you know which of the universities?
Oh,
what his lab
I can find out.
Don't worry, I can find out. I can Google it myself.
Yeah, well, if you email me, if you can't find him, I'll send you his email address. He comes to mind. I won't bother resharing my screen, but that very first series of active inference papers, he was a co-author, and he actually was the organizer of one of the very first active inference workshops about 8 years ago in Lyon, I think it was, yeah. So I haven't spoken to him for many years, but he certainly has a commitment to research in motor control, but is also well versed in the theoretical neurobiology. So
great, thank you.
that's the best person I would know. But if you can't find him, email me and I'll send you his email. And if you do contact him, give him my very best wishes.
Will do, thank you.
Also, our mutual friend Luke would like to hear from you.
Is he still at Sussex, or is he?
Yep. He's a professor at Sussex. He's French, and I've texted him to say what a great talk you gave. So
thanks.
He may have some suggestions amongst his colleagues in France. Yeah.
Yeah, brilliant. Thank you.
So he's around in the building, because I am at Sussex now.
Oh yeah.
You're in Sussex, are you?
Yeah.
Oh right, Luke.
And you're talking about Luc Moreau, right?
No, Botus.
Okay, yeah. All right.
Is it?
Yeah,
he's in computation, and yeah.
Upstairs.
He's upstairs. Yeah, I think he's upstairs. right.
He's a mathematician. Yeah.
Yeah.
So
Fantastic.
So
well, I might meet you next time I'm down there.
Great, looking forward to. With this being said, let's all give another round of applause to Nicholas for his fantastic presentation.
Thank you all so much for your super useful contributions.
Nicholas, we will upload the video online and we will share the link with you.
Yes,
All right?
I'm very happy for this to be made public. It's fine.
Excellent. Carl, you can stop the recording anytime.